We often see phosphines as a ligand on organometallic complexes and especially catalysts. And there are a few reasons for this. One of them being that generally speaking, they're chemically inert. They don't usually react with a lot of whatever we're using in our reactions. Now, there are other properties that we like about phosphines as well. One of them is that they have a very wide variety of properties that we can choose from, ranging from large to small sterics, and also from electron withdrawing to electron donating properties. And so there's quite a range of these available, and so we can adjust what's happening at the metal very finely and experiment to see which phosphine would be the best for a particular catalyst or complex, depending on what we wanted to have happen. Now, it does turn out that trialkyl phosphines are air sensitive, so that is something to keep in mind when you're working with these. They have an intermediate hardness, so not very hard, but also not a particularly soft ligand. It's kind of in that middle. The hard version of this ligand would be a nitrogen, and something softer would be further down the chart. And they have some pi acceptor abilities. These can be increased by having electron withdrawing groups on the phosphorus, or decreased by having electron donation groups on there. And this can really come from the carbon and phosphorus bond, or the bond within the ligand, and not so much directly from the phosphorus as that pi donation, because some of those orbitals on the phosphine do line up with the metal d orbitals in a more pi fashion. And it just has, it's a more subtle effect than might be seen in other ligands, such as a carbon monoxide, which has a much larger direct back bonding happening, whereas in this case, it's definitely a more mild of an effect. Now, the main bonding in between a phosphine and the metal is through that lone pair doing a sigma bond, that dative bond right here between the phosphorus and the metal. So that is the main bonding motif, sigma bond, using the lone pair from phosphorus to the metal. Now, I mentioned that we can adjust the steric and electronic properties over a wide range using phosphines. And it turns out that in 1977, Tolman published a review article on this particular topic, and he used the nickel carbonyl complex, substituting one of the carbonyls for a phosphine, and then looked at the stretching frequency between the carbon and oxygen. Remember, that is an indication of how much back bonding is happening, and if we have larger amounts of back bonding, that means that there's more electronic or more electron density at the metal, whereas if this bond is stronger, that means there's less electron density at the metal. So we can use that to probe what our phosphine is doing to the metal's electronics. So something like a trifluorophosphine would have a very strong carbon-oxygen bond here, because that is a particularly electron withdrawing group. Another thing that he did was measure cone angles, and he did this with a model, with models. And what was the goal here was to fold back as much as possible whatever ligand we have. So get this into the smallest type configuration that it can reasonably accommodate. Of course, there's going to be sterics here. And this is actually just a measure of the steric bulk of a phosphine. And it's measured from the metal out to where the hydrogens or whatever is the extreme atom on that cone. Let me get the pen to work here. It's this angle right here. That's the cone angle. Now, these cone angles can vary all the way down from about 100 degrees up to slightly over 180 degrees. 100 degrees would be a particularly small one, like this trimethylphosphine. That's a relatively small cone angle. Not a lot of steric bulk to this. All the way up to something like an X-phos ligand, where you have this bulky substituent here, and then don't ignore the T-butyl groups also on the phosphorus. This is a very bulky ligand. And depending on how bulky your ligand is, will really control how many of these can bond to the metal. This X-phos ligand is so large that only one could bond to a metal at a time. Whereas if we chose something small, like our trimethylphosphine, you can get 6 of these around large metals, such as tungsten or iridium, because those are a little bit larger of a metal. It just barely fits. Most of the time, you'll get somewhere in the middle of that, so like a triphenylphosphine, where you have the benzene rings. They're a little bit smaller, more rigid. They can be folded back a little bit more. You can get about 3 or 4 of those onto a metal. But very large ligands, again, like X-phos, or if we had a phosphine with 3 cyclohexanes or isopropyl groups, those are very large ligands, and you'll only be able to get perhaps 1, maybe 2, but usually just 1 of those ligands on there. And that can be useful, really controlling how many ligands that we have on a metal, so that we can better have control over how many electrons are on the metal. So if we want a metal to be coordinatively unsaturated, then we may want a very bulky ligand on there. That will stabilize a lower electron count. And that could be important for our catalyst cycle, because if we have an 18 electron ligand, we may not want that, because that could be very, if our first step is to do oxidative addition, then we won't be able to, because it's going to add to the electron count, and that would be unfortunate. Instead, we could put a very bulky phosphine ligand on, lower the electron count, stabilize that particular species, and then we can go from there with our catalyst. So phosphines are one of the ligands that allows us quite a bit of control over what's happening at the metal, from sterics to electronics, all while being generally unreactive towards our other reactants. So spectator ligands. Other ligands that are similar in reactivity are in heterocyclic carbenes and the cyclopentadiene ligand. Those are very unreactive, and they're often used as well because of those properties. But phosphines are very popular. Another thing that you can do with a phosphine is you can have a bidentate phosphine. And when you include a bidentate phosphine, you can choose how long of a connection you want in between the two phosphorus atoms. So if I want a particularly short connection, I can just put one carbon in between. That's not that common because this is a very short bite angle. And the bite angle is just determined by, we have our metal here, and there's our phosphorus, and then it's this angle here. So if I increase the number of carbons in between there, I can increase the bite angle. This has an effect on the orbital positions, which will also affect the orbitals on the other side of the metal. And so I can either spread those apart or bring those closer together by modifying the angle, or the bite angle. That's B-I-T-E, bite angle. This pen is giving me difficulty. Bite angle. So that is another parameter that you can change with phosphine ligands. To be fair, you can also change this with other bidentate ligands, but phosphines is one that you'll see fairly often. Common connections in between here would be 2 carbons or 3 carbons, and I believe it's in the Kumata catalyst, which is a nickel-based catalyst, that you see a 3-carbon connection where you see diphenyl phosphine. It's DPPP, diphenylphosphenylpropene. So you'd have this kind of connection. So a propane in between, and then phenyl groups on either side. And of course 2, because that will finish out the valence of the phosphorus. And then this will bond to your nickel catalyst, forming most of what that catalyst is. And you can see here, this bite angle is a little bit larger than if we just had 1 carbon in the middle. And that's the main point behind that part. So, phosphine ligands are common, and we're able to vary lots of their properties to get modify the property of the chemical, the resulting chemistry that comes from that.